morning, good afternoon, and good evening, everyone. Welcome to the fourth day of the conference now. I can't believe that now we are in day 4 or the last day of the conference. I hope you all have had a great time over the last 3 days and enjoyed the keynote speeches, as well as the technical sessions, presentations, and tutorials as much as we do. I would also like to thank the keynote speakers for their informative talk and their great contributions to the conference so far. Thanks also to the tutorial presenters for their great contribution and support. Now that we are in the last day of the conference, we also have different talks and technical sessions and also one industry forum. So stay with us. We have 3 keynote talks again today. Our first keynote speaker is Professor Pierre Luigi Mancarola from University of Melbourne, Australia. Our second speaker is Professor Yushan Chu from State Grid Electric Power Research Institute, China. And the third presenter is Professor Kongjing Kang from Tsinghua University, China. Now let's start our first keynote talk by our first presenter, Professor Pierre Luigi Mancarola from University of Melbourne, Australia. Professor Pierre Luigi is the Chair Professor of Electrical Power Systems at the University of Melbourne, Australia, and Professor of Smart Energy Systems at the University of Manchester, UK. He received his master's and PhD degrees from the Politecnico di Torino, Italy, worked as a postdoc at Imperial College, London, UK, and held visiting positions in the US, France, Chile, and China, Tsinghua University. His research interests include multi-energy systems, energy system planning under uncertainty, and reliability and resilience of future networks. He has been involved in and led more than 50 research projects worldwide and actively engaged with energy policy in Europe and Australia. Professor Pierre Luigi is author of several books and more than 300 research publications and reports, and editor of the IEEE Transactions of Power System and of IEEE Transactions on the Smart Grid, and also the convener of the CICRE Working Group on Flexibility Provision from Distributed Energy Resources, and also an IEEE Power and Energy Society Distinguished Lecturer. Professor Pierre Luigi was awarded the 2017 WESC Innovation Fellowship by the Victorian Government of Australia for his Flexity project on multi-energy urban virtual power plants, and an International Newton Prize 2018 for his UK Chile Newton PCARD project on power system resilience. Now I would like to invite Professor Pierre Luigi Mancarola to give us his interesting talk about flexibility and grid services from multi-energy systems. Thank you.
Thanks a lot, Sarah. Thanks for the kind introduction. Let me try to share my screen. I think I need some permission to share the screen.
Yeah, take your time. Thank you.
Yeah.
Good morning. Good afternoon, Pierre Luigi. I think you must be able to share now. Good. Thanks very much for joining us.
Yeah, thank you. Not yet. It still tells me that I can't share.
Can you try again?
Yeah. Yeah, now I can. Thank you.
Okay.
Thanks.
Awesome. Thank you. Thanks.
Always thanks for it. Yeah, I think now we are. Yeah, can you see my slides? Yeah, I think so.
Yes.
That's
Yes,
great.
yes.
So good to go. So again, thanks. Thanks, Sarah, for the kind introduction, for Ad and all the team for the kind invitation. I'm very, very happy, delighted to be here. It's a good opportunity to share a bit of our work that we've done over the past 10 or even 15 years, actually, since my PhD on multi-energy multi-energy systems and the application actually of multi-energy systems to, for example, provision of grid services, reliability, and resilience services. Much of the work you'll see has actually been developed in the UK. The times I was full-time with the University of Manchester, and I'm now still part-time with them. And there are now new exciting activities in this in this topic that we're carrying out in Australia. And I will show you something about this. So what I would like to cover next 45, 50 minutes is some general background in the idea of power system flexibility in the context of low carbon grids, and then how we move towards the concept of multi-energy systems and multi-energy systems flexibility, some aspect of modeling and key features of this multi-energy system flexibility, including systems themselves, but also networks. I will show some example about flexibility, for example, particularly gas networks, hydrogen networks, and this kind of applications. And then how we can extend also these ideas to planning for example, uncertain planning or a very extreme planning, for example, how we deal with extreme events that got to do with resilience. So, but you know, before I start with technical details, I just wanted to mention very nice statement was said some time ago. Water will one day be employed as fuel. The hydrogen and oxygen constituted, used single together, will furnish an inexhaustible source of heat and light, of an intensity of which coal is not capable. Someday, the coal rooms of steamers and the tenders of locomotives will, instead of coal, be stored with these two condensed gases, which will burn in the furnaces with enormous calorific power. So obviously, we're talking here about hydrogen, and I put the title "Back to the Future." Why Back to the Future? Because guess who said this and when this was said? Well, you may know it or not, but it was Jules Verne in his great book, Mysterious Island. So we're talking about 1874. You know, there are big discussions now about energy system integration and renewable hydrogen and everything else, which I will also mention later. And you know, this is like it used to be science fiction, and now it's becoming reality. It's really fascinating what we are living now. So and I hope you know that what I'm going to show you somehow will also excite you in terms of what kind of challenges we might have to deal with in the future. But really exciting. So what is this idea of flexibility? First of all, what is power system flexibility as a definition, so that I can tell you a little bit more about the technical context. We can define it in different ways. I just picked a couple of them. For example, the technical ability to regulate the power exchange with the grid. So very generic and general definition. Or, for example, this other definition, alternative definition could be the ability to provide secure and economical supply-demand balance across spatial and temporal scales by leveraging and seamlessly coordinating various controllable assets. So obviously, this by Delaunay is much more specific. It's got to do with security, economics, spatial and temporal aspects. So tell us that there are multiple dimensions of flexibility, including aspects that are related to networks, for example, that we'll show later. So obviously, this flexibility, this ability of regulating power is particularly important in the context of low carbon power systems with more and more renewables. They are partly unpredictable and very variable. So we will need, we know this, more and more flexibility, including reserves and other kind of services. But who is providing, or who has historically, I would say, provided flexibility, and with flexibility also other kind of services, security services, reliability services, because arguably you may say that anything that somehow is related to security and reliability comes together with flexibility, or in a way is enabled by flexibility, which is the ability of effectively responding to events in a more or less fast way, and consider both actually active and reactive power. So if you look at this kind of context, you will see, I provided here a sketch from some work we were doing some time ago with Tomislav Salp at the University of Zagreb, but we were trying to sort of schematically represent where flexibility comes from. And apart from sort of the obvious, I have an inflexible consumption, sort of historical passive demand, and nuclear and coal power plants, they are relatively inflexible. Then flexibility typically comes from the likes of gas turbines, combined cycles, open cycle gas turbines, and of course, hydro systems, or you could import or you could import flexibility through interconnectors. So, for example, there would be flexible generators in the United States or in another country, and then whenever there is a response or some support, this can be literally imported, so it can be borrowed somehow from other areas. What's happening in the future? Well, the moment that because of renewables, conventional generators may be displaced technically or commercially from the market, obviously we might have issues, because if these are the historical providers of flexibility and they disappear from the system, obviously we need to still provide this faster supply and demand balance, even more with renewables, the fact that we need new sources of flexibility and more flexibility because of the characteristics of renewables. So who's going to provide that if the conventional power plants disappear? And what kind of issues we might have? Well, issues are a bit obvious, like this kind of issues, and guess what comes next? Yes, and this is obviously something that we would really like to avoid. And unfortunately, this is not far future. Actually, in a way, it's already past, because we've already seen something like this in Australia, for example, South Australia blackout in 2016. Now, this is just an example, really. I don't mean that that was caused by lack of flexibility or things. No, there are different causes that you may know about, and we could discuss at length. But the idea is that clearly there may be an issue with a system that is changing very, very fast, because it's just inevitable with this huge transition that we're having, and more targets that are even more transformative. There might be problems. This problem may be associated with flexibility. So, but there is a problem, there is a solution. That's what engineers do. That's what they've done historically. And of course, who is going to provide help in this case? It's just a great entrepreneurs, and of course new technologies. So you will know that already. Actually, South Australia blackout was a big push to have towards batteries, and then Elon Musk and Tesla came to Australia, investing into the at the time largest battery in the world. And this battery system in Hornsdale is actually performing exceptionally well. So it's somehow supporting system balancing, provision of ancillary services, particularly various frequency response services, and of course it's somehow supplying flexibility, very fast flexibility. So it's really, in a way, like projecting the future, because again, if you look at the historical flow of flexibility, you may say that was going from transmission systems to distribution networks. So from a very active transmission system where everything, basically all control, was in the hands of a few conventional generators, few hundred conventional generators effectively could provide all system services, all ancillary services, and all flexibility services to consumers in distribution networks that effectively would be passive. However, now with a new system, with more and more renewables, and particularly in Australia, it's impressive how many large-scale solar farms and wind farms there are. With this system that is completely it's transforming very, very fast. As I was saying, we will require more flexibility because of more renewables. Same time, there are fewer power plants that could do that. So it's inevitable that flexibility must come from other sources. And in this sketch I put here, we basically show some potential future that it's already happening. Actually, this figure here is taken from a project. It's called the More Microgrids project. It's more than 10 years old. I was involved in this project when I was working in Pierre College, and the lead of the project was Professor Girio, who gave the keynote the other day. So I was working with him on this. It was already fascinating how 10 years ago we were sort of envisaging this future where effectively there would be distributed energy resources like the likes of flexible demand here, electric vehicles, and of course, distributed storage in support of PV plants, aggregated in microgrids would eventually, with the help of a distribution system operator that could provide somehow local balancing or check the local balancing, altogether, basically sort of set up this that today is called digital energy systems and are very much associated with virtual power plants to provide flexibility to the rest of the energy system. So these ideas are not new. They've been developed about 15 years ago, at least. But now really we see that these ideas are being implemented and the concepts are being implemented, which is great. So in a way, if you look at the future, as I was saying, coming from this research that was developed 15 years ago and then more and more to today, where these things are happening, are being implemented, then projecting towards the future, say, well, okay, we may have, for example, batteries supporting the provision of flexibility, and that's it. I mean, we're no longer worried about a low carbon energy system, right? Because we can do, we have wind, we have solar, we have batteries. Somehow we're done, at least from the point of view of flexibility. There will be other technical issues that you may know about, and I'm sure there will be lots of discussions in the conference, issues such as inertia, system strength, and all that. But no, at least from flexibility perspective, we say batteries and storage in general can provide lots of help. Not exactly. I mean, it can be, but it's not still solving the whole problem. And what is the whole problem? Well, let's look at the bigger picture. And to do this, I'm giving here the example of the UK. This is the Sankey diagram of the UK energy system, and many Sankey diagrams actually around the world. So most countries in Europe and many other countries around the world would look like this. I believe China, Brazil, the US, of course, major countries around the world will have very similar Sankey diagrams, where effectively you got input fuels and then outputs here, different sectors where these fuels will be used. And these different colors here that you can see correspond to different energy vectors. So these three colors are, one is electricity, one is heat slash gas, depending on how you look at that. The third one is basically fuels for transport. So what is very interesting in this, again, this is referred to the UK, but effectively most countries around the world got a very similar one again, is that electricity, which is this pinkish color here, is relatively small. So in terms of energy, actually the final electricity consumption is in the order of 20 to 30%. Everything else is heat that comes in the case of UK from gas, and which is this purple, and then there is this greenish color here, which is transport, is fuels for transport. So we're so worried about electricity, but actually decarbonizing electricity and then flexibility for electricity and all that, it's actually not solving any problem if the problem is decarbonization. This is what the problem of the target is, decarbonization. Because effectively, we can decarbonize electricity, but we still have 70, 80% of final energy consumption that might come from natural gas, petroleum, oil, various oil products and all that. So that is in a way motivating this idea of electrifying the energy system. Because it's okay, if I electrify heating and transport and I can decarbonize electricity, then I can also decarbonize heating and transport, which otherwise I'm not too sure how to do it. However, when you look at how big heating, how big transport, they are in terms of energy, in terms of capacity, basically becomes infeasible to have an infrastructure that is completely electrified, that is capable to support decarbonization of the other energy sectors. So the idea is not so much about electrifying, which was put forward probably 10 years ago. And again, back in Imperial College, when I was a postdoc there, actually my main area of work was understanding how you would decarbonize heating, and such electrification was not working in the UK and many other similar places. So instead of electrification, the idea is let's do integration of energy systems. So this idea of sector coupling, so coupling of electricity, for example, transport, heating, and gas, and future fuels, and then what is now called multi-energy systems, or sort of multiple energy vectors and energy sectors coming together. And like there is a form, there are a few definitions. This is definition from one of my papers that I was invited by Energy to write some time ago to sort of explain this concept that was being developed at the time. Effectively, in very general terms, you can say a multi-energy system is a system in which electricity, heat, cooling, fuels, any kind of fuels, transport, optimally interact with each other at different levels. And then this multi-energy system can be a building, can be a district, can be a city, can be a country, but the idea is how they interact, how they're modeled, how they're optimized together. So this idea really of coupling the sectors, coupling the energy vectors, coupling the systems and the networks. So when you look at this concept of integrating energy systems, what is now flexibility in multi-energy system terms? Effectively, this corresponds to different questions. For example, can other energy systems or vectors provide flexibility to the power system? So we are now we are coupling the systems with the idea of facilitating decarbonization and lowering cost and all that, so-called energy trilemma in a way. So now that we are coupling, because there are flexibility requirements on the electricity system, there will be more requirements with more renewables. Can we actually rely on the other energy systems to provide this flexibility, which effectively, like, can we use other energy systems to balance the electricity supply demand? And then on the other hand, the moment that you integrate more and more the system, can lack of flexibility in other energy vector sectors, networks, constrain the operation of the power system? So these are the kind of questions associated with multi-energy system flexibility. And there's been lots of work, various papers, sort of touching on these aspects until recently, when actually there was this paper being recently published in the proceedings of the IEEE. Again, there was an invited paper that we were asked by the proceedings to write to basically firm up this concept of flexibility from multi-energy systems, in that case, particularly from sort of distributed multi-energy systems. So in this light, effectively, the idea is, instead of using batteries, for example, or storage, like electrical storage, can be pump charging of that, can we actually, using the interface of electricity with the other energy sectors, with heating, with cooling, with transport, with future fuels, for example, hydrogen, and all the technologies that are basically belong to energy sectors, but do interface with the electricity system the moment that you integrate the systems, and use those to provide flexibility. What is the benefit of doing this compared, for example, to using batteries or pump charging or that? Basically, it's a lot cheaper to do this, because effectively, if you couple the energy sectors, and then there are opportunities that are coming from these other sectors, if already there may be embedded flexibility in these other energy sectors, you can probably be able to access flexibility at much cheaper cost than by developing specifically flexibility means in the electricity system. So instead of a battery, can you use flexibility from a building at much lower cost, obviously? I will show you some examples about this. So this is really picking up great interest. And you may know, for example, in Europe now, this is like hottest topic perhaps in Europe. And I'm very pleased about this, because I did my PhD on multi-energy systems. And when I presented this back to 2005, 2006, I mean, literally no one could understand what I was talking about. And now it's very nice to see that actually research then pays back in the long term, as we always say. This is a very important topic in Europe, I believe, also in China And now in Australia, we're getting more and more interested in this too, particularly in terms of interaction with hydrogen that, again, I will show you something about later. So when I look at this idea of providing flexibility from particularly distributed energy systems, for example, from sort of demand side, again, you can see how much of this heating, cooling, transport, it's all coming from a distribution system. So this idea of providing flexibility, not from transmission, but from somewhere else, is perfectly aligned. We say, let's also couple the electricity system with the other energy sectors, because we can actually, we will be more and more able to access different sources of flexibility. And especially when we have more and more of kind of digital energy systems where we can measure better things, it will be very beneficial actually to try to develop these concepts and technologies at scale. In terms of modeling, there's been a few models I was saying earlier that have dealt with this kind of flexibility in different ways. And then until recently, this paper where we sort of consolidated the ideas in the concept that we called multi-energy node, particularly with respect to DMS, this distance here for distributed multi-energy systems. However, in reality, the formulation that we provided is quite general, can be applied to anything. And we defined this flexibility in a multi-energy system context as the set of all feasible deviations in the flow of one energy vector from a given operating point, subject to multi-energy node constraints. So what is the idea? Imagine that you have this kind of black box that can contain networks, it can contain storage technologies, can contain different conversion technologies and so on, which you might, for example, model as an energy hub, as no, some of you might be familiar with this concept. And then, of course, there are multiple energy networks in input, and then there is some local loads and generation. So the idea is when you consider everything that is happening inside this black box, inside the hub, basically, and how can you modulate the inflow of one vector by actually considering changes in the other energy flows, and basically by somehow taking into account all the constraints that you have in the system. Of course, if this specific energy vector that you consider is electricity, then the question is, what are the boundaries of operation for my electricity energy vector that I can operate within while I'm still supplying my demand, but I'm really playing with all the different energy networks and energy vectors that are involved in the analysis. And when you try to model this mathematically, eventually you end up with classical matrix formulations that somehow is reflecting the multi-vector features of having different networks. And then mathematically, actually, you end up defining very clearly what flexibility can be in formulas. And then you are able basically to write all your system constraints and all that. I'm not going to put more formulas on this because I think that it's probably easier and more interesting to read the paper than try to explain you some very, very complex mathematical concepts here. But I hope that the concepts overall are clear. Now, where is this flexibility coming from? Because effectively, what is interesting is that if you look at individual components of the system, there is actually very little flexibility that is available. For example, let's mention here a few components. Let's say a combined heat and power plant with very sort of, this is a very canonical example, again, take it from this paper. Let's say this combined heat and power plant burn fuels and producing electricity and heat. There is an auxiliary boiler, burns fuel, for example, gas, produces heat, and electric heat pumps that burns electricity to produce heat. Then there is a power to gas component. You use electricity to produce gas, hydrogen. In case you use a Sabatier reaction, you also produce methane from that. And then there is a thermal storage device, for example. Now, when you look at this kind of setup, actually, there's not much flexibility available. And how can you model this? Well, if you assume, for simplicity, sort of linearity in these components, basically constant efficiencies, the way that you can model this is, and try to represent them all together, is by this multi-dimensional plot. So where basically you show active power, heat, and fuel, which are the three energy vectors that are involved in this analysis with the components I mentioned here. And then when you project on heat against fuel, fuel against active power, heat against active power planes, you basically have the characteristics of these components I show here. But what is the flexibility here? Because, for example, if I take a combined heat and power plant, the moment that I burn gas, then I produce some electricity. At the same time, I need to produce some heat, and that's it. So what is the flexibility? If I got some electricity demand, I got some heat demand to supply, actually there is not much flexibility at all in that. The same if I have a heat pump, I got a heat demand, I consume electricity. Where is the flexibility? If I got some heat demand to supply, how do I create flexibility? How can I change the electricity level if by changing electricity level, I also change the heat level, therefore the heat demand? Bear in mind that when you perform this analysis, you're still subject to operational constraints, right? So you have a local demand, or if you look at the system, there's still a system demand to supply, where obviously you must stay within this kind of constraints. So what's very interesting is that flexibility actually comes from the aggregation. And this is a known, well, somehow known concept when you look at single energy vectors. But then the work that we did in this paper, we actually show how multi-energy flexibility is actually coming from the integration, from the aggregation of multiple energy vectors by technologies. And how can you show this, for example? Well, effectively, when you aggregate all these technologies, this is what happens. If you aggregate combined heat and power plant and auxiliary boiler, you end up with a region that is the region that is inside this sort of purple plot here. If you look at, for example, electric heat pump and power to gas, then the operational regions become the ones that are inside the red plots. When you look at all the systems together, the operational regions are the gray ones. So effectively what we've done, we show how by aggregating components, sets of components, and then all together, you suddenly start operating within a region. So this region is what is flexibility, because effectively it means that I can now operate independently. If you look, for example, heat and active power, I can now operate independently in any of these operating points. I'm no longer linked to operating, for example, to one point of the linear plot. In the case I only had, for example, one piece of equipment. The moment I have more devices with different characteristics, I bring them together. You start having flexibility that you can show mathematically like this. Mathematically, actually, this corresponds to apply a Minkowski summation operation across multi-dimensional spaces, and of course, the multi-dimensional space would be characterized by the different energy vectors that are being considered. So, and this, of course, you also understand this actually the projections of something is a little bit more complex, which is this one. In fact, this is the multi-energy flexibility polytope that you have when you aggregate these very simple devices, and then when you project them onto different planes, like in the previous example, you have this. So it becomes really interesting because you understand now that there is no magic. Actually, flexibility is coming from aggregation. Then there are huge benefits in integrating energy systems. Why there are huge benefits? First of all, with individual components, you have basically no flexibility. So you must create flexibility by integrating. Second, the more you integrate, the more flexibility you create. And this flexibility is disproportionately larger than the flexibility of the subsets. Because look at this. let me go back. If I can go back, look at this case again. The CHP and auxiliary boiler flexibility is now these small regions here. The electric heat pumps and power to gas flexibility is these red regions. When I sum them all together, you see that you have the gray region, which is much bigger. And so the previous regions are some subsets, but the total flexibility region is much bigger. So aggregating actually enhances greatly flexibility. And now you understand why you can actually access flexibility from other energy sectors that is, first of all, plentiful, potentially. Second, in a very, very effective way, because it might be, for example, cheaper to do this. And again, if you are after the mathematical modeling, you can have a look at the paper. So when you start looking like this, you realize that now you can actually really study different kind of flexibility features that you can access. For example, say the moment that I am interacting with electricity and gas to produce electricity and heat, for example, can I shift between electricity and gas and create flexibility in input? Or the moment that I need to supply a certain output, can I transform energy vectors in a way that can create flexibility? For example, everything that we know as power to X, power to heat, power to gas, or transformation of electricity into heat gas belongs to this kind of categories. Can I play with storage, but not so electrical storage, different forms of storage, and by doing this, enabling flexibility on the electricity side? And then can I curtail some service, not again for electricity, but for other energy vectors? And by doing this, again, I generate flexibility. There are different examples of doing this. For example, a very important one that we are studying in the UK, is being studied for long in the UK, is the ability of having hybrid system, for example, to supply heat load by a heat pump and an auxiliary boiler. And therefore, you can basically shift between electricity and gas to supply heat, depending on the situation. So if electricity is cheap, for example, coming from renewables, then you use electricity. Then if electricity becomes expensive, you switch on the gas boiler. Or for example, when you may have a peak demand that is very, very high, very cold winter in the UK, for example, then you basically use the electric heat pump for base heat load, and then you top up with a boiler, so-called hybrid heat pumps. And we've done several studies in the UK, particularly for the UK national grid, and we show actually how in the future the possibility of using gas boiler as a top up to air source heat pumps, effectively hybrid heat pumps, electrical gas heat pumps, could bring huge benefits in terms of capacity that you could save. In the study we were performing a couple of years ago, the benefits would be in the order of 20 gigawatt of installed capacity. So effectively you would reduce the capacity you would need but in the order of 20 gigawatts, which would correspond pretty much to 20-25% of the installed capacity you would need in the system. So huge benefits provided by the possibility of switching between gas and electricity to power heat. Similarly, we're saying, can you use actually a form of storage that is somehow embedded in other energy vectors? Again, let's say heat as a key example. And this idea of virtual storage in buildings, where effectively you have electricity, you turn it into heat, and then you store it somehow in the building. And then because you got thermal inertia in the building, then you can play with this virtual storage from buildings. So when you do this, effectively what happens is that your virtual store somehow works as a virtual battery. What is the virtual battery operation here? Imagine that this is taken from an office in London. It's a real case. So you have a baseline consumption, for example, heat pump or air conditioning, and then imagine that you need to provide flexibility to the system. You switch off your heat pump to provide, for example, reserve service. So when you switch off the heat pump, obviously your consumption now changes with respect to baseline, but also your temperature changes inside the building. For example, if you were doing cooling with a heat pump or air conditioning, the temperature will go up because you switched off, or at least reduced the consumption of your air conditioning system. So when your service is finished, so when you basically you want to switch on again the heat pump, now the temperature has gone up, you need to cool down the environment more, because at the same time, again, the temperature has gone up. So your consumption would be higher than before. And this concept is so-called energy payback that is well known with respect to baseline. But when you do this, effectively, this is equivalent to discharging and charging a battery, right? When you compare it with baseline. Because for the system, I am consuming electricity. Switching on is equivalent to injecting power into the system. So it's like equivalent to a battery discharging to the system. Then, of course, you need to charge your battery back. And that's exactly what you do with the energy payback of the building. It's pretty extraordinary, however, that your charging of the battery is much less in terms of energy, as you can appreciate here, than the discharging. So effectively, this battery has got, this virtual battery has got efficiency of 200, 300, 400%. It's pretty extraordinary. And there's no problem with thermodynamics, by the way, because as you can see here from the title, I wrote here, comfort to power arbitrage, because effectively this virtual battery enabled from the thermal inertia of the building is costing me thermodynamically something, which is temperature. So I'm giving up temperature, I'm giving up comfort level, and this is enabling flexibility. And that's why you have an arbitrage between the power and between the comfort that somehow you are giving up. And this is all enabled by integration of the electricity systems with the heating system in this case. And if you are interested in this kind of things, you can also come up with metrics to measure that and so on. There's this very interesting word called building to grid flexibility, where we explain and model all the details of this kind of operation. The same, actually, you can do it with networks. You can use storage that is embedded in the networks to provide this flexibility. For example, and it is again, the virtual storage is in the networks. For example, if you look at gas networks, storage there is in the form of pressure, the form of line pack. And then if you change the pressures of the gas network, actually you can allow more or less flexibility in the electricity system that is linked to the gas network. If you look at a heat network, because there is lots of water in there, that's a hot water, that is effectively equivalent to having a thermal store. So you can play with the temperature dynamics of the heat networks, and it's equivalent to basically having an embedded thermal energy storage, which is the same model that basically I was showing you earlier for the virtual storage in building. Is it always good? Not necessarily, because, for example, there may be examples when you enable flexibility, but also examples when you constrain the flexibility. So, for example, in this picture here, what I'm showing you is a study that we did for the UK National Grid a few years ago, where we showed that in the future, with changes in the level of electrification, with more heat pumps and all that, and a more intercoupled electricity and gas system, there might be issues to provide flexibility to the power system from the gas network. So effectively, the moment that you have some peaking requirements from gas generators, if these requirements become very substantial, so very high ramps, very long ramps, of course, in order to provide these ramps, the generators must get gas supply. Can the gas supply, the gas network provide all the gas that is needed at the right rate, the right speed? Well, actually, we showed that under various conditions, is the gas network doesn't have enough flexibility. There's not enough line pack, there's not enough pressure in the gas network to actually do that. Therefore, you actually, if you only look at your electrical equations or your sort of optimal power flow equations, you would see that you will not be able to you will not be able to see any constraints. You will think that your system is working fine, but actually you will not be able to do that. So what we proposed in this work to the UK National Grid was to actually integrate some gas network constraints into the electrical constraints that they use for the optimal power flow unit commitment models I think in the future this will become more common practice. However, networks can also provide a form of flexibility, positive flexibility. For example, if you look at this idea of hydrogen, you use renewables to create hydrogen, and then you can inject hydrogen into the gas network and store hydrogen in the gas network, for example, for seasonal storage. Again, it's a nice idea, and some time ago we developed a module again for the UK national grid to try to understand the potential of the UK gas network to store a hydrogen coming from renewables, so green hydrogen. However, this is very much an issue of economics, as you can imagine. And now we are doing similar studies in the context of the Future Fuel CRC. We've already modeled the whole Victorian electricity and gas network. And we're now studying all the interface between renewables curtailment, production of green hydrogen via electrolysis from renewable curtailment, potential injection into the Victorian gas network. And we already have preliminary results. And what you find is super interesting, and it's really sort of complex but super interesting to see the interactions of this of the different systems and markets actually in the future. I mean, similarly, once you understand that once you have all this flexibility, now you can use this flexibility to actually play in the market. For example, provide market services. I'll put here an example of a study case in Port Lincoln area in South Australia, where we basically developed feasibility study for a hydrogen system with electrolyzers, hydrogen turbines, and hydrogen storage that in this area here that is full of renewables, but is also somehow constrained, actually can now cannot be represented as an integrated renewables hydrogen energy hub, and then operate as a virtual power plant. So the electrolyzer, the hydrogen storage, the hydrogen turbine, they're now all very flexible devices, and they are able to provide system services like a virtual power plant. And we studied actually the characteristics of these hybrid virtual power plants and the flexibility that the hydrogen could enable, that we modeled in these maps here. They are similar to the flexibility maps that I showed earlier. But in this case, we modeled this as a active power with reactive power flexibility maps. And then what we show here is how basically you have operating regions of flexibility, but also a grid services region, because these areas, if you imagine that this is your one operational point, for example, these areas that become bigger and bigger, do different colors, actually represent frequency control ancillary services potential of this virtual power plant. So there is generic flexibility. Then how fast can you provide this flexibility? This how fast corresponds to providing, for example, frequency control ancillary services. Now, with this kind of characterization, you are actually able to map this. And another example that I'm showing here is coming from the Fisherman's Bend virtual power plant. Fisherman's Bend is the new engineer campus at the University of Melbourne that is under development. So we performed a feasibility study for a virtual power plant. Is again multi-energy, because there's also heating there, cooling, and there's lots of flexibility coming from heating and cooling. And when you look at that, again, you see that this flexibility changes in time, and then it's you can really visualize flexibility and the ability of again providing these different FCAS services according to what we have in the Australian market. And of course, the very interesting thing is that when you do this, you can actually develop a business case for a virtual power plant, because now you have model flexibility, you modeled different services. Of course, you can assess the potential economic benefits, and the value actually may be quite substantial. I mean, going forward in the future, the very interesting thing is try to understand more and more how much you can integrate the systems. For example, can you use the huge renewables, huge amount of renewables you have available in Australia to generate green fuels like hydrogen, ammonia, export these green fuels, and this has been considered in the National Hydrogen Strategy, as you may know. And what we are developing, actually, we have developed a tool to assess the feasibility of these studies, particularly looking at win-win situations between renewables and electrolyzers, including export contracts. So basically, the modeling tool, which is a sort of integrated electricity, hydrogen market tools with all the system operating constraints, tells you under what conditions you can have positive payback for renewables and hydrogen exports, so that effectively all technologies and all market stakeholders are better off. It's a very complex analysis, but again, it's fascinating actually to see how it is possible to co-develop renewable energy systems and hydrogen system, including for exports, and have a win-win situation for everyone. Where okay, I will skip this. This is actually the way that we are modeling, we are mapping this cost-benefit analysis, and as I said, it's very complex. And you may have seen similar studies that are actually very simple. And I've sort of said, just don't believe it, because if you look at real market operation, real system operation, it's incredibly complex to try to achieve that. Because one of the big questions is how do you plan for this kind of system, given that there are huge uncertainty? Take the integrated system plan of the Australian system operator, AEMO. There are multiple scenarios, but then which scenario is what? How do you plan across multiple scenarios? And the moment that you have hydrogen, lots of uncertainty, how do you plan for that? So I work in the past, and we actually tested this for the UK National Grid again, with whom we have just finished a project where we have reviewed the planning methodology. Now they're changing the planning methodology. The tools to use are really, we need to move away from classical deterministic tools. We need to move towards risk-aware stochastic optimization tools. This is not to say that things need to become complex and use complex mathematical modeling. Is because there is lots of value to gain. Effectively, what we have demonstrated, and I put here a couple of papers you want to have a look. What we demonstrate is that the moment that you use stochastic tools to perform this analysis, you can actually reduce the risk of investment, and you can actually reduce the cost or maximize profits. And again, actually, the modeling work we've done is very convincing to the point that actually the UK National Grid and Ofgem, the regulator, is now actually that they're discussing basically the tools that we have developed as now potentially sort of next step in terms of implementation of planning methodology at the level of transmission system. Can we do more than that? Can we also think of what we would do for extreme events, so-called for resilience effectively, so-called the black swan events? Again, when you look at these extreme events, how do you provide more resilience to the system? Do you make the system stronger, bigger, or smarter? So do you build more infrastructure, you make it stronger, or actually look into smart energy systems? Again, what we demonstrate is that if you look at the ability of using distributed energy systems, particularly integrated with other energy vectors, particularly heat and gas, for example, by some kind of microgrids, the flexibility you can provide actually can be used for resilience under very extreme conditions. So again, system integration becomes also a form of smartness. And by the smartness, you are actually to provide more resilience to the energy system at much lower cost than you would otherwise have to do. Again, imagine the example before. Would you buy a battery if you can do the same with an air conditioning system? You already have the air conditioning. You only need to switch it on, switch it off for 1 hour. You measure the temperature indoor, subject to constraints. Once you have a digital energy system, this is easy to do. The more and more you look into this kind of flexibility and smartness, the more you realize how many benefits you could provide to the rest of energy system. Now, to conclude, because I'm seeing Sarah turning up to tell me that I'm finishing my time. So to conclude is, I would like to say that superior flexibility can be harnessed by integration of multiple energy systems. It is really coming from virtual storage ability or energy vector shifting abilities that can be provided at relatively low cost. The concept is completely scalable, can be applied at any level from building to countries to provide multiple services interacting with multiple markets. Going forward, our suggestion is to really embrace more this stochastic planning. This is feasible. I mean, we've already done this in the real world for the UK national grid. And then the moment you do this, it becomes an issue of how the regulatory and market developments can actually support the integration of all these systems. And to conclude, again, back to the future, I mentioned Jules Verne, and now I would like to mention Dr. Alan Finkel, who said, for the anxious, progress towards a hydrogen future is too slow, but look back a few decades from now, and history will record the hydrogen industry as an overnight success. So definitely, our chief scientist is a big fan of this system integration, and he's got a very bold statement, bold strategy, as you may know. So, I think we should all be looking forward to that. Thanks a lot, yeah, I'm happy to take questions now or later on. Feel free to send me emails. I'm very happy to answer questions. Thank you. Thanks.
Thank you very much, Professor Luigi. It was really interesting, very impressive. Thank you. I really enjoyed it. Now the panel is open for questions.
Let me stop sharing, perhaps.
Yeah. Can I ask the first question?
Please.
When you were talking, actually, presenting, the part of my question was answered. I was going to ask about the hydrogen, and at the end of the presentation, I had my answer. But anyway, I just wanted to ask about the feasibility of hydrogen and how feasible about when I think about the risks and in terms of the restrictions that there might be. So how do you think about the feasibility of the hydrogen?
Yep.
How can we?
Yeah, that's a great question. So it depends on how you interpret. For example, we have done extensive studies for the Future Fuel CRC in Victoria to study the capability of injecting hydrogen inside the network and studying basically if the pipelines can actually accept hydrogen, because there are lots of material issues and all that. What is the ability of the system to accommodate that? Effectively, the feasibility itself from a network perspective of injecting to gas network up to 20% seems now widely accepted, and our studies for system perspective suggested that there would be no issues. Then now the question is becoming more, could the appliances actually support this mix of hydrogen and gas? This is being studied. The other option would be, can we move towards a system that doesn't have this mix of electricity, of gas and hydrogen? Can you only have hydrogen? But of course, you would need to reconsider then how do you build a new network? Do you do it in the distribution network where, for example, plastic pipelines that they could accommodate this better? But there are lots of technology aspects that are very, very complicated. On the other hand, if you look at export, I think the export is a little bit easier from a technology perspective, is more apart from shipping that is being studied, but it becomes more an economic issue, and that's why I was presenting a kind of integrated market tool where we study effectively the win-win situation for different cases. But I am very positive, and we are basically the next 2 years with the Future Fuels, we will hopefully be able to answer these questions with numbers and not just with some sort of hypothetical thinking that we have at the moment.
Yes, because I actually heard about even electric vehicles, and everybody says, say the electric vehicles are just moving so fast, but I heard even hydrogen is just taking over, so we might actually go.
And it's a mix. It would be a mix. Surely it would be a hybrid portfolio. As I was showing, it's by integrating different systems that you create value, you create flexibility. It would certainly be a hybrid portfolio and a big mix, I would say.
Sure. Okay, let me just go for first question here in the discussion session. Thank you very much for offering the excellent keynote speech regarding the flexibility in an integrated electricity and thermal system, considering that the response of the electricity system is very quick, while that the thermal system very slow. From the electricity system operation, perspective, could an integrated electricity and thermal system provide realistic flexibility?
Absolutely. That's exactly where flexibility coming from, is the fact that the thermal system is slow that enables flexibility. Imagine that, having a slow thermal system effectively means that you have an equivalent store there. So being very slow, basically there are different time constants, very fast on the electricity systems, very slow on the thermal system. So any change that you do at the interface, the thermal system doesn't see it because the time constants are much bigger. So the fact that it's a slower system actually enables at the interface that you have very fast responses at the interface, and the thermal system doesn't see it. If actually you can change, you can switch off a heat pump instantaneously, right? You switch it off instantaneously. So you are providing a flexibility service basically as fast as a battery. If you keep it off for 5 minutes, is anyone going to perceive a temperature difference for 5 minutes that something's been off? Not at all. That is exactly because the time constants of the heat system are much larger, and the thermal system is much slower. So it's a misconception where you need to look at this from the right perspective to understand how these fast and slow characteristics actually play together. But that's really where flexibility is coming from.
Thank you.
Thanks.
And yeah. Oh, sorry, I was just missing the questions. There are just many comments. Thank you very much for the presentations. Thanks a lot for the great keynote. Thank you very much for the great presentation. It is great to see hydrogen is marching on. As mentioned, economy is an issue. How the policy is moving forward in regards to manage the cost economy. Also, what is the progress on the, I can't read the rest.
Yeah, I can start to respond
yes,
to this,
sure.
perhaps. I think economics is essential. And unfortunately, as I was saying, I think it's problematic when I've seen many simple studies, just say, if electricity is this cheap, electrolyzers are this cheap, job done. This is very simple. A market doesn't work like this. We need to think of a market where you have huge, for example, for export, you have huge electrolyzers that are flexible loads. Actually, these electrolyzers will play in the market very differently from the kind of demand that we see today. In fact, that's a very elastic demand. So the interaction of a relatively inflexible system with a very elastic demand is something basically we don't see in the market. So you need this kind of new tools to assess that. And when you look at that, there are actually few conditions by which both the electricity systems, a decarbonized electricity system and a hydrogen system can play together. And you need to find these right conditions, but it is possible. And what is very nice is that you can try to co-develop the two systems together. Therefore, the aspects of regulation, energy policy, and market design are essential. But we need to forget that this is something simple. It's complicated, and we need to accept it like this. But that's why we do research, and we hope that we can support actually the regulators in this kind of endeavors.
Sure, thank you. The next question, is energy efficiency a part of integrated energy system and demand flexibility?
Yeah, absolutely. I think the first thing we need to do is to try to reduce demand. And when you integrate systems, a big benefit that you see, in one of the papers that we wrote with Thomas Sapud, actually, we show exactly that when you integrate, actually you reduce capacity of the system. So by reducing capacity, you are already providing some form of energy efficiency, because effectively now you are sort of optimizing your resources, you're optimizing your assets. But in any case, I think that that's always the first step. The first sort of flexible or useful renewable piece of kilowatt hour is the kilowatt hour that is not used at all. So energy efficiency really plays an important role there.
Another comment and question. Thank you very much for interesting and informative talk. I would like to know that in multi-energy system, how the thermal system can provide reactive power flexibility in addition to active power, which is easy to perceive?
Yeah, so no, thanks. So in that case, the reactive power flexibility is always coming from the electrical equipment. So whatever electrical equipment you have in there is characterized by active and reactive power. So the moment that, so the thermal system somehow, thermal and other energy vectors enable active power flexibility. And then once you have this active power flexibility, then you also have reactive power flexibility that somehow is attached to this active power flexibility, but it's a function of what the electrical system does. But because now the active power is coupled to the other energy vectors, also reactive power somehow ends up coupled with the other energy vectors. And in the multi-energy node formulation, when you write equations, this is clear. But in reality, the flexibility from other energy vectors is really on the active power, and then there is this interaction between reactive and active power coming together on the electrical side.
Yes, the next question. Thanks for an excellent presentation. Is there a link between the stochastics and the dynamics of the various energy subsystems? For example, the different types of generation, storage, and load?
Yeah, no, thanks. So the stochastic aspects that I mentioned towards the end, I guess the question refers to that, is really long-term planning. So for long-term planning, so at the moment, if some of you are familiar with, for example, the integrated system plan of IMO, there are different scenarios, and then you plan for different futures, and then somehow you need to consider these futures together. And what they do, they use a kind of least worst regret analysis, which was somehow taken from what UK National Grid was doing for many years. Now, recently, I said we've done this project with UK National Grid, pushed by the regulator Ofgem, that they would like to see more sort of probabilistic planning to be considered rather than deterministic as it is today. And then from our previous work, what we show is that the moment that you consider this stochastic programming techniques, so the fact that the future is uncertainty, and you can use mathematical models to sort of model this uncertainty, you can actually come up with solutions that on average, and from a risk perspective, are much, much better than decision theory techniques that you would employ for deterministic planning. So it's really, in a way, the mathematics that you build around it. But again, it's not to say that we want to do things more complicated. Actually, we want to do things cheaper. And that's why, you know, even the regulator, of course, now is conservative by nature, actually. He started getting convinced that there are different ways of planning, not only under deterministic rules.
Thank you. In dynamic simulation of an integrated energy system, considering that the time constants among electricity, thermal, and transportation differ significantly, how could efficient simulation be carried out?
Yeah, so that's nice. That's a nice question. People have discussed a lot this kind of multi-physics simulations. If actually you can try basically to also with different simulation tools, try to simulate independently the different systems and try to soft couple them. And then, for example, you can simulate the electricity systems depending whether you want to do dynamic or steady state analysis. Let's say classical steady state analysis like power flow analysis every, say, 5 minutes. And then, for example, the heat system every 30 minutes, 1 hour, the gas system every few hours, every day. And then you try to couple them together. So we've actually done this depending on the use case. And I would advise everyone to look into it if you're doing this kind of modeling. However, the key point is whether you can somehow operate with these different time constants, but in an integrated way, and you got ways of writing these integrated flow equations, integrated optimal power flow equations in an efficient way with different time constants. And actually, we're working on that. We are going to write soon a tutorial paper on how to model this kind of systems together with the different ways. It's an important piece of work. It's an important question. So glad to hear these kind of questions and people are working on this.
Thank you. Again, one comment. Thank you very much for the excellent and comprehensive presentation. You mentioned that the more multi-energy sources, the more flexibility we have. I'm wondering the practical solutions for dealing with uncertainties introduced by integration of different energy resources, for example, renewables. The investment to integration of multi-energy resources comes from fiscal investments or from free market in your framework.
Yeah, so that's a good question. I think, I mean, all the modeling we've done is all based on sort of techno-economic and commercial modeling that is realistic in market environments. So there's always a case of saying, is this a sort of least cost investment, for example, or can you make money in the market and can you develop business cases around that? So what we show is actually that by creating flexibility from system integration, if you are in a market environment, you can provide system services, and by providing system services, you basically improve the business case of what you're going to invest in general. So again, by creating flexibility through energy system integration, you also improve the economics of the system because you can participate in different markets and all that. From the point of view of the resource, if you look at this from a system perspective, because you integrate and because now you access sources of flexibility in an integrated system at potentially lower cost, obviously the whole system cost of the integrated system will go down. So it's also beneficial for the system. You can look at this from a cost perspective or sort of commercial perspective, different points of view, depending on the kind of market or context setup that you may have. But the results won't change because integration and flexibility bring values regardless.
Thank you very much. Okay, I think that was the last question.
Sorry, do you mind if I jump in and just first, thank you very much, Professor Pierre. That was a very fantastic and excellent talk and very great presentation. Thank you. I do have one very quick question, and that is, you mentioned about like your involvements with the projects on this multi-energy system levels in UK, and I assume that probably very similar investigations and studies are going on in across Europe, and I'm aware of similar type of projects in China. How is the situation in Australia? I mean, are here the people are working on that multi-energy optimization and planning, or is it more like so is it again very integrated type thing, or is it more separate?
Yeah, thanks, Fad. I think at least from what I've seen, there is really huge interest is growing in interaction with electricity with hydrogen, and this is, I think, the main form of energy system integration we're seeing. However, people also talk a lot more about sort of sector coupling, which is naturally got to do with heating, including for industry and electrification of industry and all that. So it's, I think, a little bit of a different perspective to what we're seeing in the UK and the rest of the world. But there are definitely similar studies. I think, again, we'll see more and more that there is value in thinking more holistically, not just on the electricity system, but really looking at also the interfaces with the rest of the world.
Yeah, absolutely. I definitely agree. And probably, as you said, there is a great area of work in this possibility of that for Australian context, definitely.
Yeah, absolutely.
Okay, I think, yeah, if there is no question, yes. Thank you very much. Oh, yeah, question is here. Thank you very much for attending the conference and for your very interesting presentation, for your contribution in this conference.
Thanks to you. It was a pleasure, really. Thank you.
Yeah, I myself, yes, please. Oh, yeah, I myself, on behalf of, again, myself and the entire organizing committee, I also thank you very much for your excellent talk, for joining us, and for your great contribution. I enjoyed your talk a lot, and I hope that all the delegates have enjoyed it. And it was obvious from the question and answers as well that it became very interactive. So thank you very much for your kind support.
Thanks, Farhad. Thanks, everyone. It was a pleasure again. Thank you.
Thanks very much.
It's a good rest of the conference. Thank you.
Thank you. Thanks very much.
Okay, everyone, I think it's time to move towards another keynote to speak. It starts in 15 minutes, if I'm not mistaken. So I will see you. So you have to actually, again, disconnect and connect if you click on the link in the conference program booklet. I will see you soon. Thank you.
Thank you.